So the beginning point to analyzing this is to first consider the aperture field. The incident field, as we just pointed out from that TE01 mode, is given by this expression, and this exists in the throat of the horn before the flare starts. An educated guess for the field in the aperture is this. So a guess for what the aperture fields look like is that they are y-hat polarized, just as the incident fields are. We have this constant E0, just as before. And now what we're going to say is that the aperture field scales with the dimension little a becoming big A. So that's obviously a little bit of a guess, but I'll come back to that in a moment. And then we'll tack on a geometrical optics phase factor, accounting for propagation from the throat to the aperture. Now this is a somewhat bold assumption, but it's generally validated by experiment. We find that this is a reasonable assumption, that is simple propagation from the center of the throat, and the somewhat stranger idea, simple extrapolation of the throat distribution into the aperture distribution, as indicated by this part of the expression, that turns out to be a pretty reasonable thing to do. Again, I wouldn't expect anyone to take that for granted if they're encountering this for the first time, but it holds up when we actually analyze these things more rigorously and also when we do measurements. So I'm asking you to accept this now, and I'll show you examples of how good it is later in the lecture. So now let me do this trick. I'm going to re-reference the phase distribution to the center of the aperture. In other words, here it's kind of awkward because the zero phase point is in the throat, and I would prefer the zero phase point to be in the aperture. So all I'm going to do is take this phase factor and subtract off the distance from the throat to the center of the aperture. And then I'm going to note that I can rewrite this distance into the aperture as follows. R becomes the square root of x squared plus r1 squared. And now this should account for the variation in phase due to different distances from the throat to the aperture. In other words, I have a relatively long distance here, a relatively short distance here, so this phase should be less than this phase. Or rather, the phase I accumulate here should be less than the phase I've accumulated here because the path length is longer. Okay, so the radiated field. Let me first say there's several ways to deal with this. First, you could just do it numerically using a full wave solver. I'll come back to that idea at the end of this lecture. It's not really what we want to do here because we can learn a lot by looking at approximations to these expressions. Your textbook does this one way, and I'm going to do this a different way. The way your textbook deals with this problem is to first assume a quadratic phase approximation, and that is, it looks at the phase dependence that we just worked out, this thing here. You can rewrite this. Then you can invoke the binomial approximation, where you assume that x is much, much less than r1. In other words, the dimensions along the aperture are less than the distance from the throat to the aperture. And if you make that assumption, you can invoke the binomial approximation. That eliminates the radical, that is a square root operation, and you end up with a somewhat simpler expression. Then the second thing your book does to try to get a closed form expression is to invoke the transverse electromagnetic field approximation. And this is the assumption, if you remember, that in an aperture, E and H lie in the plane of the aperture so that the pointing vector points broadside to the aperture. So you can invoke the transverse electromagnetic field approximation and then get this expression, which we have previously found using aperture theory, where these variables here, px and py, are spatial Fourier transforms of the aperture distribution. Now that's pretty dicey here. And the reason is because if you believe everything we've just said about this approximation for the aperture fields, you would really expect S, that is the pointing vector, for any ray traveling through this to actually be slightly off broadside. So this should work relatively well if the aperture is small compared to the throat aperture distance. But for practical horns, you're certainly on the edge of being invalid. And it's not really an approximation you have to make. It gives you slightly nicer expressions. And the technique I'm going to use, I'm not going to make quite a radical approximation. In other words, I don't like this part. So the cost of doing that is I'm going to come up with somewhat more complicated expressions. But I think that's okay. My summary statement to you is go ahead and look at how your book does this, and then also look at the way I'm doing it. You'll see what you win or lose by making various kinds of approximations. Okay, so here's my approach. We'll use full-blown type 1 equivalence. If you're murky on what that is, I'm sure I've discussed that in a previous lecture, and you should go back and refer to that. But the idea is that the total field, radiated, is the sum of the electric field from electric currents plus the electric field from magnetic currents, magnetic equivalent currents. Here is a perfectly reasonable expression for the field radiated by the electric currents from aperture theory, where Q is a spatial Fourier transform. Here is a perfectly reasonable expression from aperture theory for the electric field from the magnetic currents. Again, we see components of the spatial Fourier transform over those currents. And just to remind you, here are explicit expressions for the spatial Fourier transform. So here's P and here's Q. Again, P is the spatial Fourier transform over the electric field in the aperture. And then Q is the spatial Fourier transform over the magnetic field in the aperture. We can work out P sub y, the y component of the spatial Fourier transform over the electric fields in the aperture. Making the substitution, we get this expression. We can pull E naught out because that's a constant. This is an integral over the aperture, which is x going from minus a over 2 to plus a over 2. Y going from minus b over 2 to plus b over 2. Here is the expression that we have developed for the field in the aperture. And then here's our phase factor, written now in terms of theta and phi. Now we can factor this out into two integrals, one over x and the other over y, as indicated by the breakout in square brackets here. Now, if you look at this expression, it looks pretty complicated. If you look at this expression, it should look somewhat familiar to you. In fact, as I say here, this is an old friend from aperture theory. We know this is going to give us a sink-like result. This other integral can really only be done numerically, at least as far as I know. So I'm going to give this a name so I don't have to keep writing the whole expression out over and over again. The name I'm going to give it is capital I sub p, and this is a function of theta and phi, so I've indicated that explicitly here. So now whenever I refer to I sub p, theta, phi, it's this integral evaluated at theta and phi. So I can write now the result. The y component of the spatial Fourier transform over the aperture is E naught times this numerical integration that I have to do, times the dimension, times the sinc function that we knew was coming. And just to remind you, V is defined as sine theta sine phi. So that should be familiar to you from aperture theory, that sinc aspect of it. We can do the same thing for Q. Q sub x is given by this integral. I need an expression for H. So all I'll do here is come up with an expression for H from the plane wave relationship, take the dot product to get the x component, and this immediately gives me minus E sub ay divided by the impedance of the medium, which is probably free space in most problems, times cosine alpha, where alpha is, as we've defined it all along, the angle here measured with respect to broadside. And I can make that substitution and work through the integral, and I get this result. All right, so I'm skipping several mathematical steps here, but they are fairly straightforward. The end result is a constant, an integral which I cannot do in closed form, which is defined here, and a sinc-like function, where once again, V is sine theta sine phi. So now I've got the electric field. I start making substitutions. I get that the electric field due to electric currents is this. The electric field due to magnetic currents is this. Now the total field is the sum of those two things. So the result looks like this. plus jk E naught, where k is, as always, the wave number, 2 pi over lambda. I get a spherical wave. B, the dimension of the waveguide in the E-plane. A sinc function. And then this combination of factors. The theta hat component is a function of the I sub q integration and the I sub p integration. And the phi hat component is also a sum of the integration I sub q and the integration I sub p multiplied by cosine theta. So this you can all, of course, verify. And by the way, another useful thing here to do is to make sure this is dimensionally correct. That's another good way to check the result. So that's a complicated expression. So let's see what that looks like in the H-plane and the E-plane. In the H-plane, well, in this geometry, that corresponds to phi equals 0. We know it's proportional to this expression. We don't have to carry through all the constants in order to determine the pattern. We only need to carry through the factors which are going to change because everything else will disappear in the normalization. I can write out these components that remain, the y hat, the integral over x, and then the rest of the factors here. In the E-plane, phi equals pi over 2 in this geometry. That's theta hat polarized. So I get the sinc function and then these two factors. And again, you can verify this for yourself. Simply set phi equal pi over 2, the previous expressions, and verify that you get this back. I can write this out as follows. Theta hat, the sinc factor, then an integral that looks like this, which we're going to have to do numerically. So I can plot those things. In order to plot them, I have to choose some sample values. In this case, I'm going to choose a horn which has r sub 1, that's the distance from the throat to the aperture, of 6 wavelengths, a aperture which is 4.5 wavelengths wide, and the dimension of the waveguide in the E-plane is 1 wavelength. So these are pretty typical for a H-plane sectoral horn. And then I can plot the normalized field patterns, and they look as I've shown here. This blue curve is the H-plane. This red dashed curve is the E-plane. And you see there seems to be a modest amount of directivity here, as you'd expect. But I also point out that the H-plane half-power bandwidth is narrower than the E-plane half-power bandwidth. And that's what we expect, because the H-plane corresponds to the plane in which the flare of the horn exists, whereas in the E-plane we have no flare. So we expect to see a narrower pattern in the H-plane than in the E-plane, and this is a characteristic of an H-plane sectoral horn. Now, as usual, we're interested in directivity. So I'll just remind you, a completely reasonable way to calculate the directivity for this would be to first compute the beam solid angle. That's simply integrating over the square of the normalized pattern. And then to compute the directivity using 4 pi over beam solid angle. In this case, it's pretty tedious and not really necessary. It's tedious because you have to integrate to get the normalized pattern function, and then you have to integrate again to get the beam solid angle. Instead, we can invoke the transverse electromagnetic approximation, the very same approximation I spoke ill of a few slides back, but for getting the directivity, it's not a bad way to go. Essentially, when we do this, we'll be ignoring the fact that the magnetic field intensity in the aperture is partially polarized outside the plane of the aperture. This is the problem I pointed out on the previous slide. As long as R1 is much greater than A over 2, it's not such a bad thing to do, at least in terms of directivity. I'm not sure it's such a good idea for pattern. In any event, the expression to use is this one, which we've undoubtedly talked about in a previous lecture. You can compute the directivity under these assumptions as being 4 pi over lambda squared times the ratio of these integrals. I can show you some examples. In this case, I am choosing a value of b, that is, again, the dimension of the waveguide in the E-plane, and that's going to be 1 wavelength. I'm going to choose R1 to be 6, 10, and 15 wavelengths. The result I just showed you for pattern was R1 equals 6 wavelengths. And then I'm going to show you directivity as a function of the dimension of the flare part of the aperture. So in the previous example, I worked that out for A equals 4.5. So that the horn that we analyzed for pattern corresponds to this point here. So that has a directivity of 34 something in linear units. If we increase R1, we see that directivity increases. That should be expected because as we increase R1, the aperture is getting bigger. But we see that as we increase the overall size of the aperture, A, there's a distinct trade-off. And it's the one we pointed out earlier. If A is too small, we end up with low directivity. Eventually, we hit some optimum value, and then if we keep increasing A, the directivity falls off again, this time because of phase cancellation in the aperture. So there will always be some optimal value of A for any given choice of other parameters at which we achieve the best possible directivity, and that's typically what a designer is looking for. And by the way here, I should point out that all these results scale linearly with B. The reason is B appears as a factor in the electric field expression.